Hello, my name is Valter Ruotila. I'm a research assistant in the Unified Database Management Systems research group at University of Helsinki. Jiaheng Liu is a professor specialized in databases and the leader of the group. Dieter Gavlik, Zhenhua Liu, and Suripriya Das are database architects at Oracle, and Gregory Bogossians is a database specialist at SEAData' Technologies. Warmly welcome to this presentation, Multimodal Query Processing meets Category Theory and Functional Programming. The topic and the presentation are connected to the demo system called Multicategory and a paper which are part of this year's VLDP demos. The outline of the presentation is the following. First, we represent a short introduction to multimodal databases and say a few words about the role of category theory in our work. We describe the demo system shortly, then we show some challenges related to the current multimodal databases and generally to modern database management systems. After that, we propose solutions to these challenges and vision new features that these modern systems should implement. We argue that these new features are answering the challenges that modern database applications are facing. We can start by asking, what is a multimodal database? A multimodal database is a database management system that has a single unified backend that can handle multiple models. Sometimes multimodal database refers to a database that can handle at least two different models, for example Postgres. In this sense, most modern databases are multimodal databases. But more often, we require more properties from multimodal databases. Here is an example of a multimodal data environment that includes, for example, some relational, graph, and XML data, and some relationships between these datasets. The models can also include text, images, audio, video, spatial, expressions, and other complex data structures. Some commercial multimodal databases are Oracle's Converged database, ArangoDB, and MarkLogic. Another big topic in our work is a category theory. So what is a category theory? Sanders MacLean and Samuel Eilenberg introduced categories in the mid-40s as a mathematical tool to study algebraic topology. This makes it a relatively new field of mathematics, but it has been very successful. Countless areas of mathematics have been starting to use the category theoretical approach to do mathematics. The key idea is that many concepts in mathematics follow very similar structures. Thus, those things can be unified. Why do 100 different things separately when you can do it once and generalize it? Then people notice that category theory can be applied widely outside pure mathematics. Possibly the biggest application field is computer science. Some examples are databases, programming languages, especially functional programming languages, natural language processing, and quantum computing. And some concepts that category theory uses are categories, functors, and natural transformations. And an interested reader, viewer, can read more about this from any standard category theory textbook. And we have developed a demo system around these category theoretical ideas and multimodal data management. The demo is part of this year's VLDP. The backend of the system is implemented with the functional programming language Haskell. We model queries using fold mechanism from functional programming, which also can be described using category theory. And the demo utilizes so-called schema and instance categories, which provide us a unified view to interpret different models and instances. The data instances are modeled as functors, which are structure preserved mappings between categories. Now we represent some challenges of multimodal databases. Besides the property that a multimodal database has a single unified backend that can handle multiple data models and formats, we require other properties from full-fledged multimodal databases. We require that it implements a single declarative query language that can perform cross-model queries. This means that the user can access multiple models in a single query. The extended versions of SQL are cross-model in some sense because they support query in JSON and XML along with relational data. Then we require a property that is addressed quite rarely in multimodal databases, and this property is a unified indexing mechanism. The indexing should be such that it can index data across the models. And depending on the use case, we might need to change the representation of the data often, and it should be performed efficiently. This is why a multimodal database should implement extensive and automatic data transformations. So we have this intuition in mind that we have relationships between datasets, but those datasets are following different models. So the question would be like how to join these datasets over some relationship and what does it even mean? We can easily find countless ways to combine different datasets. So does there exist some formal way to describe these multimodal joins? And maybe can we generalize the idea of relational join to multimodal instances? And then we represent some challenges of modern database management systems. So we identify that the end user's experience is often poorly addressed in the design and implementation of modern database systems. For example, NoSQL is mainly targeted for developers. Technology is supposed to evolve according to the business and end users' needs. One of the problems that we have been discussing is so-called catalog problem. For example, a customer has an empty spot in their home and they want to buy a suitable colored, sized and shaped sofa to that spot. So how to design a system that where you can execute a query which can combine the information, all of this information, and find a suitable sofa to that spot. And then how to generalize this approach to any product. So historically, relational databases weren't the first databases. The first models were hierarchical and network data models, and after them, the relational model was invented. Currently, we have reinvented the hierarchical models as JSON and XML, and the network models as RDF and property graphs. And every model has its suitable use cases. This has caused that the database zoo to expand in a way that makes it difficult for end users to navigate and choose suitable systems and models. NoSQL system complicates the matter by forcing user to access data without a declarative language in a very loose transactional system. All of these efforts have regressed the usability of databases. And in practice, the data is never static. The temporal dimension of data is often poorly implemented in databases. Next, let's proceed towards solutions to the presented challenges. The principle of databases is that there is no single data model that is the best or the worst. Therefore, it's time to introduce the concept of a virtual data model. A modern database should provide the concept of the virtual data model to the end users. The virtual data model design could be similar to the concept of virtual memory in classical operating system design, or it could be similar to the virtual machine in modern cloud computing environment design. It is up to the database to autonomously decide what data storage formats are used underneath the cover. The choices depend on the use case and the database access patterns. Inside the database, it may maintain multiple data models and formats on disk or in memory. The modern databases should support both schema first and schema later paradigms. We could approach that from a document store model perspective. Then we could extend a declarative query language, for example SQL, with suitable extension functions to query and update schemaless data. Besides, we could adopt relational indexing and inverted indexing strategies. This would bring schema first and schema later approaches closer to each other. As we noted before, the temporal dimension of data is often poorly taken into account in databases. In order to make the temporal features of databases better, they should be able to create and access the complete history of data. Besides, databases should be able to inform relevant parties in real time of any changes that happened to the data. It is possible that the time component is difficult to model theoretically. For example, a part of temporality is event detection, which could be theoretically tackled by developing a calculus logic on top of queries. All in all, the current constraint of fixing one single storage data model and schema-first data access without temporal dimension needs to be relaxed for modern users. The modern databases would benefit from the unification of metadata and data to define schema-flexible storing, indexing, and querying features. NoSQL databases are already providing this unification, and it's good to continue on that. Over 40 years of success of relational databases has demonstrated that the principle of declarative query language and transactional multi-version concurrency control are good properties for users to access data. All of the proposed features and properties make the multimodal databases more complex. This creates an urgent need for a better theory to formalize the systems. Relational algebra and relational databases are based on set theory. Set theory certainly would work here as well, but most probably its notations and reasoning would be heavy and theoretically difficult to manage. Thus, we propose category theory as a foundation for a new query language design. Category theory could create foundation to model query processing and transformation frameworks for modern databases. Finally, we proceed to the conclusion and present some future work. Multimodal databases and other modern databases are facing lots of challenges. We want to emphasize the importance of the end user's experience. To address these challenges, we have proposed a virtual data model and gave ideas on how to better implement the temporal dimension of data. We argue that the declarative query languages and transaction management are still wanted properties from modern databases. One part of the development is the fact that the systems grow more complex, which creates a need for a better theoretical framework. Recent progress in applied category theory has shown that category theory is a very powerful framework to model, and it can be used to define complex systems formally. Our future work includes researching more the represented challenges, which include data integration and migration, transformations, modern query languages, temporal aspects of data, and the virtual data model. In this work, we believe that we can utilize category theory. Thank you very much.